Okay. Well, welcome to the first of our seminar series for the spring semester 2009. I'm thrilled to be introducing Steve Centuria, who was a member of our faculty for 35 years before retiring in 2002. He has won all sorts of honors, including being a fellow of the National Academy of Engineering and fellow of the IEEE, and has also served as the chairman and chief technology officer of Polychromics, a company built on some of the technology he's going to talk about today. Special thing about this speaker is that this is the first of a rare double feature for the speakers in our series. This is the first half. He gives a talk on his research. The second half, exactly 3 months from today, is a performance. 2 months. 2 months from today, April 24th, is a performance as a clarinetist with the MTL chamber players. So that performance will be fascinating. This performance will be fascinating. I hope you enjoy them both. And can we please welcome Steve Centuria.
Thank you. Thank you, Joel. It's very nice to be back in the room where I tortured students for so many years. My hope today is that this will not be torture, but it will be fun. Is this height okay? It's okay. All right. I will trust you. So this is the outline I'm going to follow. By the way, I should say something about this CTO thing. What does that stand for? It stands for Chief Talking Officer. So I talk a lot about what Polychromics does because it's pretty neat, as I think you'll see. So here's my outline. I'm going to introduce this bizarre concept of peanuts versus pyramids, and then I'm going to spend a moment on some of the economic issues around MEMS. And I'm going to illustrate those ideas with 2 case studies. One is a silicon microphone for cell phones, and the other is the Polychromics phaser for materials analysis. And at the very end, I'm going to look briefly at what they share. And they really do share some important things. And I just want to acknowledge right at the beginning that Peter Leppard of Knowles sent me a bunch of slides that I could use, and I appreciate it. So, peanuts versus pyramids. Okay, what am I talking about here? Well, let's first of all ask, what do peanuts have to do with MEMS? Well, first of all, the market size might be comparable in billions per year, or for peanuts it's probably trillions per year, maybe hundreds of trillions. In this era of stimulus spending, trillions and billions get mixed up. The price is very cheap. You can get them for peanuts, in fact. I mean, they're cheap. So that's what I mean by, that's the peanut size. Big market, cheap price. You can get them not too expensively. Well, what about pyramids? Pyramids are a little different. The market size is somewhat limited. I don't know if you've ever bought one, but it's somewhat limited. They're not very transportable either, but that's a different issue. The price is also not so cheap. When I think about the pyramids in Yucatan that I was climbing over in January, it's probably price measured in human lives, which is not so kind a thought. There are lots of non-peanut parts, okay? For example, there's this guy down here sitting at the base of the pyramid reading something. I don't know what he's doing, but this was the photo I happened to find, so be it. Now, the analogy I want to make between a MEMS product and a MEMS-enabled product is the MEMS-enabled product is an inverted pyramid held up by a really strong peanut. I will say that twice. A MEMS-enabled product is an inverted pyramid, meaning it gets wider as it goes up, and I will illustrate that, held up by a really strong peanut. Okay. So let's get this contrast clear. If we think about MEMS as regular peanuts, the product is the MEMS device. The markets are measured in millions or billions of units per year. The emphasis is on low price, and therefore it has to be on low cost, unless, of course, you're running a charity, which most businesses prefer not to do. The component gets incorporated into many larger systems, and I'm going to illustrate that with microphones, but the same could be true of pressure and acceleration. For example, you talk about an accelerometer, the first mass market for the accelerometer was in the automotive airbag deployment. It was a mandated market. As a mandated market, it justified investment to meet cost and performance requirements. And then, lo and behold, the shaky video cameras started to put accelerometers in them to do compensation for camera jitter. And now you can go bowling with a computer, thanks to, the Wii thing has a lot of accelerometers in it, and so on. The accelerometer is still the accelerometer, and the people who make accelerometers. They don't make Wii or some of the other things. They sell components. The MEMS, however, as really strong peanuts, the MEMS in that case have to enable some unique product capability. The markets are measured in thousands of units per year, not millions. So there's 3 orders of magnitude minimal difference between the market sizes. The value of the product, which incorporates the MEMS, greatly exceeds the value of the MEMS. And that's a good thing, because then that gives you some room in your gross margin to pay a little more for this MEMS that has this unique feature. And those are the 2 sides of the economic model that I want to talk about. The mass market, cost-driven, huge product volumes component versus a product that has some important functionality which is enabled by MEMS but might not have a very large product volume. So, here we go, MEMSonomics 101. I will make an assertion which you can challenge if you want by going out and starting a company and proving that this is wrong. In order to build MEMS reliably, you have to spend $1 million a year, on the order of $1 million a year. I don't care whether it's dollars, euros, or Swiss francs. You take your pick. Not yen. It doesn't work for yen. You have to 100 million a year for yen. Because you just have to do that, because you have to keep a process running and have it be stable and manufacturable. In order to do this, you're going to have a certain number of runs, and in order to have a certain number of runs, you're going to have to spend a certain amount of money. And that's just the way life is. Now, for the MEMS commodity products, the peanuts, this is not cost determining. You can use a captive fab, or you can go to a vendor. It's a make-buy decision of the kind that companies make all the time and are very good at. They make a decision to have an in-house fab. Okay, they know the capital investment. They know how much product they can push through. They know how to amortize it. They can make a decision about doing that as opposed to going to some vendor who has enough manufacturing capacity for their anticipated product volume. And it's a very straightforward decision. That doesn't mean the solution is easy, but it's the kind of decision that managers really understand perfectly well. For the MEMS specialty products, this is cost determining. The fact that you have to spend $1 million a year of either dollars, euros, or Swiss francs means you're going to have to spend that whether you can sell the product or not. And therefore, it tends to convert what you usually think of as a part or component price into a fixed cost. And this changes a lot of the break-even analysis that you do about products and how you have to price them. I mean, if you sell only 1,000 units a year and you're spending $1 million, then you could argue that the cost per unit sold is $1,000. That's a lot. It's a lot more than a peanut. So I made up some numbers, and I have to make sure I have to make very clear these are made up numbers, because these are not from Knowles Microphone Company. These are numbers I made up, but sort of illustrate how these numbers work. Let's assume that you're building MEMS devices on a big wafer, and it's a really small part. And so you can get 40,000 parts on a wafer. Your wafer cost is $8,000 a wafer. That's not a crazy number. Let's say you've worked at this for a while. You have an 80% on wafer yield. So your base cost is then 25 cents per part before packaging. And these are plausible numbers. Let's suppose you're selling 20 million a year. That means you need 625 wafers. That's all. 625 wafers, which is about a 12-wafer lot per week, which is keeping the factory going. Every week you start another 12-wafer run through the line, and you're emerging at a rate that corresponds to 20 million devices a year. So the total cost that you're spending on the MEMS before packaging and test now, this is just for the chip, it's $5 million. You notice that's bigger than my 1 million limit. And it's clearly that 1 million is not cost determining. It's the volume you're making that's cost determining in this case. So now let's consider the specialty MEMSonomics under a fantasy scenario. And the fantasy scenario is that you have finished the research and development. That never happens with a MEMS specialty product because you never make enough of them to get out of the development cycle. But let's pretend that I passed through the looking glass into Wonderland and we finished the research and development on a product. 200 parts per wafer, big chip. $3,000 per wafer at a vendor who's doing you a real big favor. Because at $3,000 a wafer, they're not making much money, but they want your business because there's an economic downturn and they're worried. You have a 50% on wafer yield, which is actually pretty good for one of these specialty products. And the reason I say that is since you never really get out of the development cycle, you haven't gone fully up the yield learning curve at any time for any product ever. So 50% is an estimate. And let's assume that that gives you a base cost of $20 a part, by the way. $20 compared with 25 cents. The message is coming through, I hope. Let's assume you can sell 1,000 a year. All right? You only need 10 wafers. Can you imagine going into a vendor and saying, I want to establish this relationship with you. I want you to make my parts. They say, how many wafers are you going to run? I need 10 a year. They show you the exit. Because they say, I can't, for 10 wafers a year, I can't maintain a manufacturing process. How can I can't do that. Goodbye. So what you do is you go into a ballet. It's a ballet in which you promise to do some research and development along the way, and you promise, therefore, to keep a certain minimum number of runs going, and then you default on that promise once they're hooked on you. Okay, that's the way it really works. But you do have to build more than you can sell. And this is the point I really want to make. You can't sustain manufacturing with 1 wafer lot per year, but you can with 4 or 6. So if you ran, for example, 4 10-wafer lots per year, this has raised your cost of fabrication to the point where it's a fixed cost in how you figure your operation. Your company has to pay that whether you can sell the product or not. It is not a variable cost that grows with product volume, because you have to grow product volume a long way before it would show up as a variable cost. And so it ends up being part of your enabling cost rather than a component cost. And a lot of people have trouble with that when we talk about products. I mean, the total cost in this trivial example is $120,000 or $120 per part sold. And that's cheap for a MEMS specialty product. Much more likely for a MEMS specialty product to be talking about $400 or $500 per part sold. In other words, that's what the accountant would like to put in the cost of goods sold, but you've had to build more than you can sell, because that's life. Okay. Well, under these circumstances, knowing your market size suddenly matters a great deal as to how you approach trying to make a real MEMS product. So the first question to ask is, what makes a MEMS device market worthy? And this is a list that I concocted of things that make a market worthy. If it creates a wholly new market, that's really a good thing. Well, it's a double-edged sword, actually, because if it's a new market, you probably have to go educate people about that market. So there's a marketing cost associated with educating future customers. But if it opens up a new market and people get the wind that it's a new market, then you're in good shape. Another possibility is that works better than the corresponding thing it's trying to displace. A very good example of that is a silicon pressure sensor, which completely took over the low to medium performance pressure sensor market, not because it was small, not because it was made of silicon, but because it just was working better for the price that could be bought. I mean, it's just a good product. Same is true for the accelerometer. Another possibility is that it satisfies a critical size requirement. I always like to think that size can matter. It can. An example is the blood pressure sensor that has to go inside a small tube and used for in vivo use. It doesn't actually go in your body, but it goes in a catheter attached to your body, so it has to be small. There are certainly examples where the size could matter. Or it could have to satisfy a critical speed requirement. And an example is, that I could give is the use of the Texas Instruments mirror display for projecting images, where the fact that you can flip these mirrors really fast enables you to get dynamic control of the grayscale in an image with a very small chip. And it works just fine. Ultimately, though, it has to reduce customer cost in some way or provide some benefit to the customer at a price he's willing to pay, and that's always the bottom line. And then this is the really irritating one. The product has to work. And you say, that's absurd. Of course products work. No, they don't always work. If you can't meet the spec that the customer has, it doesn't matter whether it's smaller, faster, sexier, cuter, cheaper, doesn't matter. And the example that I like to pull out is the MEMS DC relay. And I'm trying to think back, the first time I think I saw an example of a DC relay in MEMS was more than 20 years ago. And I do not believe you can purchase DC MEMS relays today from anybody, because in spite of 20 years of effort and development and work, they still do not work well enough to displace a mercury-wetted relay. It just doesn't work. So when they get there, they're going to sell like mad, but they're not there yet. Now, there are also some interesting market dynamics issues that have to be considered. My buddy Kurt Peterson says that a MEMS-based product has to satisfy what he calls a starving market. Somebody has to really want what you do. Now, one of his examples was the anthrax sensing system that his company Cepheid had made about the time that the anthrax scare lit up the post office. And the post office is still one of Cephid's best customers, because they were able to provide a solution to the problem of evaluating mysterious white powders for anthrax. Another example that I like to use is the famous optical cross-connect switch, which a lot of companies built. And they work. They really work. They really do connect fiber optics to each other just like they're supposed to. The problem is no one would buy them, because they all came on the market in about 2000, 2001, 2002, at the point at which the telecom market was cascading towards Earth at a collision trajectory. And so the sidewalks are littered with the names of OMM, Network Photonics, Onyx Transparent Networks, Kairos, Lucent, ... Many companies that tried to make optical cross-connect switches went bankrupt, or got sold or closed or whatever. So now let's get on to the case studies. I'm going to look at these two examples. I'm going to look at the silicon cell phone microphone. Now this is a device that is trying to displace an existing product, which is the electret capacitance microphone, abbreviated here ECM. The market price is set by the ECM. The potential advantage that the silicon microphone has is that it can withstand the solder temperature for surface mount technology, and therefore has the potential to lower the overall customer cost by permitting a low-cost manufacturing method to be used instead of hand assembly. Now, if the hand assembly is done in China where no one gets paid fair wages, okay, that maybe electret microphones will work. But if you want to automate the assembly and use so-called surface mount SMT technology, then you can manufacture anywhere. The machine just runs in places and you're fine. The point is, though, it must compete on cost, whether it's component cost or overall customer cost in manufacturing the cell phone or whatever it is that's going to occupy or contain that microphone. Now, the other example I'm going to use is a completely different story. There is no portable handheld spectrometer until this one came along. And the spectrometer does things that is different from what existing laboratory instruments do, and therefore there were many markets available, but it opened up a new market, and that's good, and at the same time it requires educating customers. So let's start with some pictures, and again, these are all from Peter Leppert at Knowles. These are different connection styles for the competition. These are Electret cell microphones, Electret capacitance microphones. They come in all different shapes and sizes, and depending on the shape and size they're in, they have to be attached to the circuit board in different ways, and it's very often by hand assembly, which is labor intensive and also not very reliable compared to what you can do with surface mount. A few words about the market, and I should say that these numbers could be badly out of date in that Peter provided me this data a little over a year ago, so you have to allow for some growth in these numbers since I got them from him. But at the time, we were talking about if you're going to do surface mount, which is what the silicon microphone can do, the market is approximately, was at that time about 1.1 billion cell phones, 100 million cameras, 100 million Bluetooth setups, 100 million laptops and computers and stuff, a sort of 1.5 billion unit accessible market, but you have to sell well below $1 per microphone, and the exact prices he was a little cautious about giving me, so I respect that issue, but this is certainly a ceiling on the price they could charge. At the time he gave me these slides, Sysonic had about 95% of the MEMS market, and they had sold, as of February 2007, 550 million pieces. So this is a peanut for sure. It's a good peanut. We're going to see how good it is as we go ahead. The issue was the packaging about the ECM version. It wasn't surface mountable. But now there are some surface mountable ECMs, but there are still multiple connection schemes. You have to worry about acoustic sealing, and you need rubber mounts for vibration. So the issues associated with the microphones, temperature range, humidity, whether vibration sets it off, is it sensitive to RF, how does it respond to supply voltage variations, 2 wires, 3 wires, are there any added functions you can put on, and so on. I'll make a small diversion. One of the interesting things that happened to me when I became more involved in commercial products compared to research on campus was the two different brains that are often used by people evaluating problems. In the university environment, you hear, well, I have this neat idea for a gadget, and then you go find a market where it might apply, and you pick out the top 2 or 3 market specifications, and you say, well, I can respond to those, therefore that's a justification for going ahead and working on it. But out in the commercial world, specification is a chart this long, and if you don't meet them all, it doesn't matter if you meet 3. And you have to think differently about technologies that may or may not be successful because they have to meet all of the customer requirements before the customer will accept them. And so such things as how is its humidity sensitivity could be critical for an application, even though you have the sexiest microphone on earth. If it doesn't have appropriate humidity and sensitivity, you can't sell it. You can make it, but you can't sell it. So this is what the silicon version looks like. It's fully surface mountable. It's a 3-wire interface, power, ground, and output. It's shielded, which means RF that would be present in the cell phone doesn't disturb it. And it has virtually no vibration sensitivity. And the reason for that is a MEMS issue. It has a very low mass. It has a relatively high resonant frequency. And vibration occurs only below about 10 kilohertz. And if it has a resonant frequency above that, it doesn't respond much to vibration. This is a real match head. This is not a big match. That's a regular match. And these are what the devices look like. You can see a cavity on the back, And you can see on the front a circle with a little stick coming off. And I'm going to show some more pictures of this. I'm going to say a minute about the assembly process, though. This is assembled onto a circuit board. So there's the MEMS chip, and there's a CMOS chip, and then a lamination of 2 pieces of circuit board with appropriate adhesives, and then a top lid with a hole so the sound can get in. And the MEMS is the most expensive component here. The FR4 circuit board is cheap, and CMOS is cheap, and a little plate is cheap. So the MEMS is the most important. This is a cross-section of the two-die solution. The base is a circuit board. CMOS chip is glued down. The MEMS chip, which I schematically indicate with a diaphragm, this is not how it looks. I'll show you how it looks. And then you wire bond from the chip to the CMOS, and then from the CMOS to the circuit board, and the traces come out for contact. I guess they come for surface mount. They come through to solder bumps on the back, and then you can surface mount. The circuit board itself is made in 4-inch by 4-inch panels. It's FR4, which is the standard epoxy circuit board. It's been around for years and years. You use standard die bond, wire bonds. You assemble all the stuff on it, and then you separate the individual devices. And this has the virtue of not having to handle lots of small parts. You can assemble right onto this FR4 board all the pieces, wire bond, put the lids on, and then you saw them up and they don't get dirty. And here's some pretty pictures. This shows the MEMS chip and the CMOS chip next to each other. This is a bunch of them together, and this is a pencil lid, and that's, again, a real pencil. It gives you an idea of how small these things are. So my notion of 40,000 on an 8-inch wafer is not crazy. I want to now take a look at the MEMS chip and look at some of the details of the design of this microphone. I have to have an equation because it's a technical talk. Okay, it's my equation. For a capacitive microphone, you put a voltage on the capacitive microphone and you look at the time rate of change of charge because the capacitance is changing. And so if the microphone is biased at constant voltage, the current in the microphone is proportional to the bias voltage times the time rate of change of capacitance, and that's how it works. If the diaphragm moves, you get a change in capacitance. Okay. Now, the Knowles version of the microphone has a big etched out area, and it has a diaphragm, and then it has a backplane. The backplane has a bunch of holes in it to optimize the squeezed film damping of the motion of the diaphragm. And if you take a close-up look, you see there are a bunch of these posts between the backplane and the diaphragm. There's a post and the diaphragm. Now, when you operate this thing, the diaphragm, I didn't show it on here, but the diaphragm is really a circle with one stick attaching to the surrounding. And they call it the lollipop design because it's one stick. It's like a big circle on a stick. It's a lollipop. So it has this one connection to the rest of the structure, but the structure itself is very floppy, and they have to stabilize it somehow. But you have to put a DC bias on the microphone to operate it. So they had this very clever idea. Let me use the bias to pull the diaphragm in contact with some insulated posts, and then the diaphragm will be held at a fixed position relative to the diaphragm, relative to the support, and it'll bend a little bit in response to sound, but it won't go anywhere. It'll be fixed. So these posts form a ring providing support, but along the way, the stress in the diaphragm, whatever stress may have been created in this thin film device when you put it together, is completely relaxed. There are no stress issues. And that's a huge win. This is a more detailed cross-section. This shows during fabrication. This shows after release. This is the diaphragm here, okay? And there are these posts, and you create contact with the DC bias to stabilize the diaphragm against the posts so that it's supported like a ring. It's like I guess I'm thinking of a trampoline with posts around it, lots of posts. Okay. And this, again, shows a close-up of one of the posts and the diaphragm and their relative proximity. More photos. You can see the damping holes here for the motion of the diaphragm. This is the backplane. Diaphragm is through that hole. It vibrates up and down, and the damping is controlled by the density and displacement of and distribution of these holes. Now, The thing about the lollipop design is that it allows complete stress relaxation so that the boundary condition at the edge is just a fixed point. It's just sitting. It's not pulling. There's no stress in the diaphragm. As a result, you get a pretty good sensitivity because there's no stress stiffening of the response of the diaphragm to a change in pressure. If it was a clamp plate, if you clamped it, the stress in the diaphragm would make it much stiffer and much harder to move. And in fact, this boundary condition is very interesting. It's sitting on a post, which means that it can bend with almost a non-zero angle right at the post. If it was clamped, it would have to curve like that, and that would make it a little stiffer and a little less sensitive. So these little tiny details involved in the design of the diaphragm and its support all are gauged towards getting its sensitivity up and getting it vibration insensitive. There's a factor of 3 improvement almost or almost 4 improvement in displacement when you use just a simple support as opposed to a clamp support. Okay. What I tried to get across was that this microphone has to work, and there's a very intricate mechanical design underneath to make it work, a very cost-effective packaging scheme that permits it to be sold in competition with electret cell microphones. And so what I'm going to do now is change gears rather abruptly and talk about the near-infrared spectrometer that Polychromics is now selling. This is a benchtop spectrometer, $100,000, $150,000 FTIR system you can buy from half a dozen companies. There exists a backpack company that has what we call a luggable, and then there's us. And this is a 4.5-pound, looks like an electric drill, and it's a complete infrared spectrometer. I'm going to show you how it's put together and what's in it, and a few things of what it does. But this 4.5 pounds, I should say, in 2 weeks we're announcing a 2.5-pound version, which is quite impressive. Okay. Near-infrared technology, a little bit of background here. The optical spectrum, of course, runs from the sublime to the ridiculous, but if I look at between UV and IR, we go through the ultraviolet, the visible, and then the infrared is thought of as having 3 bands, roughly, so-called near-infrared, mid-infrared, and far-infrared. And the frequency range, the wavelength range we're talking about is 750 nanometers to 2.5 microns, so it's a near-infrared. Now, why is the near-infrared important? One of the things is that all chemical compounds have vibrations, and some of those vibrations produce an oscillating dipole moment. If they produce an oscillating dipole moment, they can interact directly with an electric field and absorb energy, and so they will absorb light at frequencies that correspond to vibrations that have a time-varying dipole moment associated with them. Now, therefore, if I can look at the spectrum of light, I may be able to get information about the chemical composition. And this is true in the far infrared, the mid-infrared, and the near-infrared. Now, the mid-infrared has a lot of detailed information about chemical structure. And that's what most people think about when they talk about doing an infrared study. They look in the mid-infrared. The near-infrared has some commercial advantages that are very interesting. One of them is that the vibrations the absorptions occur at harmonics of the fundamental vibrations and at combination tones, beat notes, if you will, between vibrations of different frequencies. So the near-infrared spectrum has got features all over the place that are indicators of a few constituent vibrations that are occurring out in the mid-infrared. So there's a richness of information available. The second thing is that the absorptions tend to be relatively weak. Well, that's hard because it means you have to build a good spectrometer, but it gives you an interesting advantage, which I will comment on again when we talk about our search for illicit drugs. Those of you who wonder where this is headed, is we're headed into the drug wars of Mexico, okay? So this is the infrared analyzer. We call it a phaser. That's short for Polychromic's Handheld Analyzer Infrared, but what it really is, it's a takeoff on, what is it, Star Wars, Star Trek? Okay, Star Trek, okay. And it includes a spectrometer, a light source, a probe, a computer, a display, rechargeable batteries, and it's fully programmable. And here's the point. Instead of bringing samples to a laboratory, you bring the laboratory to the sample. And if you can make the laboratory light enough and have enough functionality, you can do that. And that's what Polychromics has done. The core technology is old news to an MIT audience, at least those of you who have been around long enough. This is a device, it's called the Polychrometer. It was developed here in collaboration with Honeywell and Sandia Labs. The last PhD student to work on it is Eric Deutsch, who's sitting right there. And so I'm going to show some of his slides. Imagine that you have a whole bunch of parallel piano keys. And in cross-section, each one of those piano keys is sitting on one of these very intricate supports. You'll notice it's a two-level support. When I apply electrostatic actuation to the support, the lower beam bends. This moves down, but the top surface remains flat and parallel to the substrate. So I have like a piano key on an elevator. It stays flat and parallel to the substrate. This is very important for its optical performance, because if they're all at the same height and I put light on at normal incidence, it just reflects back. But if I depress every other one by a certain distance, then when I put light on, it diffracts away. So I have a light valve that I can control simply by vertically displacing every other piano key. That's the idea. Okay, and then this, I have to do this with this. Okay. This will just show you, that's just a schematic of the actuation process. You can see that the top beam stays flat and parallel to the surface. And you can put different voltages on the different beams and control the way it operates. So that's the message there. Now, this was developed, I said, at MIT, Honeywell, and Sandia under a rather large DARPA program. It was about $8 million over 5 years. We were working initially in the 3 to 5 micron range and then in the 8 to 12 micron range because we wanted to build infrared spectrometers. Now, Polychromics was started to work in the telecom business, which is not at 3 to 5 microns or 8 to 12 microns. So I'm going to show you first what was developed for the 8 to 12 microns. Then I'm going to say some words about what Polychromics built. Because it turns out it's a lot easier to build one at 1.5 microns than it is to build one at 8 to 12 microns. But the pictures are better for the 8 to 12 micron ones. So the idea is that the travel you require is at least a quarter of the longest wavelength, better half of the longest wavelength. So if you're doing 12 microns, you need to get at least 4 microns of travel to have anything interesting. The diffraction angle, where you diffract the light away, is determined by the beam pitch. The spectroscopic resolution, if you will, is determined by the number of grating elements. And by the time we did the analysis under this DARPA program, we wanted to make 512 beams, 20 microns wide and a centimeter long. Think about that. 20 microns wide and a centimeter long, and it moves like this. It's a pretty challenging task. And so how do you do that? Well, you get a really good graduate student who's sitting here, named Eric Deutsch, and we worked in collaboration with Dan Youngner, and we came up with a design that really worked. The critical thing was we had to control the tensile stress in the polysilicon that was used to make the structure to a very, very tight window. It had to be within 5 megapascals of 15. And that's an extremely challenging manufacturing requirement. But we needed it, and we were able to get it. But it was very important that stress control is the key here. Among the different things that we had to worry about was, how do you make something that long and have it actuate well? Well, you make a bunch of identical cells, and you line them all up, and you operate them in parallel. Then you can do it. We separated the electromechanical actuation from the mirror. The lower beam is the electromechanical actuation. The mirror is the upper one. We worried about stress transfer, stress control, stress compensation, stress, stress, stress. We also had to have a thick sacrificial oxide because our gaps are big. And that's where graduate students are really useful, because they'll go back to the place, put 2 microns down, anneal it, put 2 more microns down, and 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 anneal it, and finally it's ready. And you can't do that in manufacturing, but in development it was fine. And he did graduate. Okay. These are just some SEMs to show you the intricacy of the structure. This is a post. It's this post here, and then the lower beam is here, and the mirror beam is up on top. These are photographs from our original work with Honeywell. I don't have corresponding photographs of the Polychromics chip because they're not so interesting and not so beautiful. But the thing to notice is this bridge support. The posts go over the electrodes. There's a lot of intricate detail there. You can see here the supporting point between cells is a post is built in multiple pieces, so you get good tensile stress transfer across this joint. And you have to also tether the ends of the beams so that they don't sag due to tensile stress. A whole bunch of different design features that have to be incorporated into this. Now, this upper gap between the mirror and the actuation beam has to be at least 4 microns, and the lower gap has to be bigger than that, because you don't want to have electrostatic pull-in. And it has to be at least twice as much, so it has to be at least 8 microns. We did 10, and that's where we put 2 microns of oxide down at a time to get a 10-micron gap. But the structure ends up having a bonus. This is a very simple schematic of the pixel structure. And if you imagine actuating it, the lower beam bends and the upper beam comes down. But then there's a point at which the upper beam makes contact with the supports. And when it makes contact, the whole structure gets much stiffer. So it's much harder to get it all the way down to the electrode. It's like a built-in protection against accidental collapse. And that's, in fact, the way it works. This is data from Eric's thesis of the displacement in microns of the gap as a function of applied voltage. And you can see that as you increase the voltage, it moves down, moves down, moves down, moves down, then it touches. And when it touches, instead of just this curve continuing down to catastrophic collapse, it's stiffer, so now it goes more slowly. And as long as you design your power supply so that you can't ever get to the end of this curve, you never have a problem with these things pulling in. It's completely robust against pull-in. It's a very good design. So now I want to take this device, and I want to think of it as the base of this inverted pyramid. And I want to think about the different layers that are in the pyramid. First of all, you got the MEMS itself, and I claim it's a really strong peanut. It does survive 30,000 Gs, by the way, so it is really strong. And then you have to put it into a compact optical design to make the spectrometer, and I'll show you what that looks like. And then you have to have a modulation method that enables you to collect the spectrum. I'll show you what that's like. And then you have to have low-power electronics, because remember, this is going to be a battery-operated instrument. Low-power electronics that do the actuation, the control, and the signal acquisition. And you put that, you control it with firmware that controls the instrument, but then you have to have software that's tailored to the particular material identification need of a customer. The Mexican government wants to find heroin. Shaw Carpets wants to know whether this is a cotton, wool, or nylon carpet, and if it's nylon, is it nylon 6 or nylon 6.6? These are completely different applications. They can be handled with the same instrument, provided you put the correct software in it. So we've become a software company to a very great extent, and then you have to package everything in a customer-friendly, rugged, ergonomic design. All of that has to happen before that MEMS chip takes on any value at all. And this is the real point I want to get at in this general idea of what I mean by a MEMS-enabled product. The fact that you can build a MEMS doesn't do you any good unless you can do all of these other things well. And then it takes on significant value. Okay, this is the optical design. It's pretty simple. You take your light, whether through a sample or reflected off a sample, you put it on a fixed grating, which disperses different colors onto different sections of the MEMS chip. And you use the MEMS chip as a programmable light valve, either to reflect the light back to the detector or to diffract it away. So it's either on or off. We use it in a digital mode. And then we can implement something called digital transform spectroscopy. Now, this is a somewhat complicated chart, but I'll go through it with you. Each one of these rows of dots, a green dot means that the pixel is on, meaning the light is being reflected back to the detector at a certain range of wavelengths. And a white dot means that that pixel is off, meaning the light in that set of wavelengths is being diffracted away and does not get to the detector. And time is running this way, and so we go through a sequence of 100 different patterns of 50% of the pixels on and 50% of the pixels off. And that creates, at the detector, a time signal. Looks like this. Time is running downhill. And then there's a very simple transformation from which you can then produce the spectrum. So it takes 100 settings of 100 pixels, tracking the light at the detector all the while. You get this time signal. Take that time signal, apply the transform to it, and you have your spectrum. Works. Takes about a half a second to take a spectrum. And then you have to put it all together in a rugged package. And this is just an exploded view to give you an idea. This is the optics module there. That's this part. The MEMS is inside the optics module, but you have to have a battery, you have to have a trigger, you have to have a light source, you have to have collimating light, you have to have a display, you have to have a whole bunch of other things to make it into a product. And it's an interesting thing. The optics module that we came up with, because we were in the telecom business for a while, we learned how to make things rugged. And so our spectrometer is actually space qualified. So it's going to the moon. The LCROSS mission, which is supposed to have launched last October and hasn't launched yet, is going to look for water in the lunar crater somewhere on the south pole, near the south pole of the moon. The idea is you have two space vehicles, one of which crashes into the moon and kicks up a plume of stuff, and then 20 seconds later, a second one comes through and takes spectra as you're heading towards the moon, and then it has to collect the spectrum, analyze it, telemeter the data back before it crashes into the surface. So this is a do-once experiment. But here are the two spectrometers in the spacecraft ready to go, but there are other complications. I guess the Russians are doing the launch or something like that. Anyhow, it hasn't gone up yet. It was supposed to go up last October, and we're waiting. When we get water on the moon or not, we will tell everyone. Okay, I want to say a couple words about the programmability and how you create the final application that's useful. What you do is you collect spectra on samples you know, and then you do some analysis to find linear combinations of the spectral features that identify and classify one type of material versus another type of material. It's a form of simple pattern recognition, if you will. Then you load that into the instrument and you can analyze samples. Now you'll notice in this example, the instrument is being used through the plastic bag that holds a white powder. I mentioned earlier that in the near infrared, the signals are somewhat weak. That means a thin plastic bag doesn't absorb enough light to disturb our measurement. So we can look at a powder through a plastic bag without opening it. Now imagine that you're at a customs warehouse and you open somebody's suitcase and there's a plastic bag of white powder. You just look at it. A lot of arrests, but I'll get to that. I'm going to just show a simple example. Identifying sugars. This is a whole bunch of different spectra of about 6 different sugars that were taken with the phaser. They're taken at different angles in different containers, and you need to allow for the noise that might be present in analyzing a signal. So we collected all those, and then you find the appropriate linear combinations of spectral features that separate. Now, in this case, the sugars, it takes 3 different linear combinations of the spectrum. That is, you take treat the spectrum as a vector, and you have a matrix with 3 elements in it that computes the projection of that spectrum onto 3 axes. And once you know those 3 numbers, all of the sucrose ends up in this hyperspace part, and some of this, all the glucose ends up here, and all of the lactose ends up here. You load that linear transformation into the spectrometer, and then you look at the bag, and it says, okay, this one's sucrose. Works fine. We have one for sugars. We have one for fabrics. We have one for narcotics. Okay? Well, you may wonder, how did we get these spectra? And the answer was with great difficulty. because we do not have the legal right to have the samples in our facility, and we don't have a controlled substance license or anything, so we had to find a friend. And we had a friend. Friends come with 3 letters in their name. I'll leave it at that. But we took the spectra and we analyzed them and created about a 50 material library that we loaded on the instrument. And the Mexican government last fall bought 49 of them and put one in each one of their customs depots. And a couple weeks ago, I got an email with a press release that a 300 kilogram load of pseudoephedrine was seized from an Air France flight, and I think it may have even made the newspapers up this way. And they said that it was due to the fact that they were able to use our instrument to detect it. Now that's a precursor for methamphetamine, so it's a sort of raw material for the drug industry. And so we're very much engaged in the war on drugs in Mexico. But there are lots of other interesting applications. Explosive detection. We have a library for explosives also. It has 70 materials in it. And this was developed in collaboration with an organization that's related to the CIA, but we don't know exactly who it is. Our contact is with an arm of the CIA, and then they say, you go to these meetings and they say federal government on their badge, you don't know where they work. Anyhow, they have this. Huh? CIA. And there are lots more applications, and I'm just going to talk about one more before I conclude. And that is a very important one called incoming raw material verification. And I'm going to focus just on the pharmaceutical industry out of all of these possible applications. At the present time, if you get a 55-gallon drum of a powder and it says something, magnesium stearate, on the outside of the box, the requirement that's coming down in the EU and in Asia and will eventually be in the US is you have to prove it. So you have to open the container, open the plastic bag, take out a sample, label it correctly without making any mistakes, carry it to one of those $150,000 lab instruments, stick it in, measure its spectrum, verify that it's magnesium stearate, which is a boring result, carry it back, make sure that you get back to the correct 55-gallon drum, check it can be removed from quarantine and allowed to go in the factory. That's typically a minimum 2-hour process, subject to all kinds of errors, and you must open the liner. The alternative is you pop the lid, you put our thing in, you point, you shoot, you're done. This is a pretty good sales argument, and it's starting to work. We're starting to see significant penetration in the pharmaceutical market just for that simple task of raw material identification. At any rate, that's one example of a MEMS-enabled product. And what I wanted to end with is what do these two examples have in common? What do they have in common? What did I emphasize? They both had to have really exquisite mechanical design of the underlying MEMS chip. Whether you're making a peanut for a 1 billion unit sale, or you're making a product that has to have some functionality that enables some big inverted pyramid, you still have to do exquisite mechanical design, know your materials, understand stress, do all of the things that you learn in class about this stuff, and do it well. Critical attention to stress control. Both applications were driven primarily by stress control issues, and it just permeates the whole thing. And my bottom line here is that both peanuts and pyramids require maximum brain power. Thank you.
Okay, we do have time for just a couple of questions. I wanted to start with one actually, which that, Steve, I noticed when you showed the picture in kind of hyperspace that the clusters were very small and very far apart.
Right.
So that would mean that your identification error rate.
Sugars are really easy.
Okay.
Yeah.
Is that fairly typical
No.
of this? No.
No. I'll give you an example. One of our important markets is the carpet recycling. When you tear the carpet out of a building, it can be recycled, provided you know what the fiber is. Well, if it's a wool carpet compared to a nylon carpet, that's easy. But if it's a nylon 6 versus nylon 6/6, that's hard. And our software to do that separation is actually a two-step analysis. We first identify it as a nylon, and once we know it's a nylon, then we apply a new second algorithm, which does a more sophisticated analysis as to whether it's nylon 6 or nylon 6/6. They differ only in the substitution on the main nylon chain, and you have to be able to tell them apart. And you have to be able to make that measurement in the presence of water vapor, because the carpets are typically wet, and the customer requires that we report how much water is in the sample as well. So
Do you have to be able to make the right call, say 70% of the time or 90%?
95+% of the time. In the carpet market, I actually have statistics. They did 95,000 measurements and had 17 misses. Okay? So it has to work really well. And in the narcotics area, it doesn't have to work quite as well. Narcotics area, they're willing to do more testing. They want to know, is there some heroin present, or is there some cocaine present, or is there some pseudoephedrine present, or methamphetamine, or any one of the 50 or so compounds we have in the library. And if it's a mixture, they're willing to do a little work. But if they don't see anything suspicious, then they can just release it without having to do the test. So, and that's the same thing we have a version for asbestos as well, for analyzing for asbestos. It's the same deal. If you don't see anything that looks like asbestos, you feel pretty good. But if you see a casing on a pipe and you shoot it, it says at least 5% asbestos, you know you have a problem. So it's good as a screening tool for that application as well.
Okay. Can we take one question from the audience before we wrap up?
All the way in the back.
Doctor, so far as narcotics or explosives, how small things can be picked up at a small, say,
We cannot do trace analysis. If what you're asking about is, can we do trace analysis, the answer is no. There are other methods, like when you go to the airport and they take a wipe and they put it in a spectrometer. That is a different kind of analysis technique. We can look at materials more in bulk. You need to have enough material in effect for the light to penetrate, be absorbed, and re-emitted back at your detector. And that is typically not a trace coating. We also cannot do very well trace contaminants in an otherwise pure material. For example, you all know about the melamine scare in pet food, and it came in a pet food precursor. And the limits of detection on the melamine were very small, and a trace amount of melamine in something else we had trouble doing. We're not suited for that. We're very good at the sort of gross material analysis. We're not so good at trace quantity analysis.
Okay, we have to wrap up. Let's thank our speaker one more time.
Okay. I'll stay around for a minute. Sure.